Should I start or you want to introduce?
Well, we should introduce you at least the first time.
I'm sending money found reminder.
Okay. All right. Well, it's a pleasure to introduce Professor Helena Judith Lopes from Rio, who's going to tell us she's going to give us 3 talks this week: conservation of energy, weak transport, and vanishing viscosity in 2D. Please.
Thank you, Idris, and thank you for the opportunity. It's a real pleasure to be here at the INI. Okay, so first of all, let me tell you a little bit about the topics that I'll be discussing in these lectures. So I'm going to talk about behavior of conserved quantities when flows are not smooth, flows are irregular. Mostly I'm going to be talking about 2-dimensional flows, which is the only thing for which I can actually prove the theorems. And we're going to be talking specifically about energy, LP norms of vorticity. All right, so the concerns in my talk are, first of all, there are too many weak solutions. We're talking about Euler here. So I want to look at vanishing viscosity. Solutions that arise from the vanishing viscosity limit, do they give us any more information than we had before? Is there some kind of selection criteria? That's what we're looking for. Okay. In the back of my mind, there are issues in turbulence. So dissipation versus energy conservation, and entropy conservation. All right, so let me fix notation here and tell you what you all already know very well, that the equations that model unforced incompressible fluid flow are just the system of equations, ut plus u grad u is minus gradient pressure plus mu Laplacian of u. Divergence of u is 0. U equals 0 corresponds to the Euler equations, ideal or inviscid fluid flow, and u greater than 0 model from Navier-Stokes equations. So in this audience, everybody knows this very well. I'm just fixing notation here. Okay? All right. Now we're going to go specifically to 2D. And so first I will call the 2D curl, which is just this scalar operator here, grad curve dotted. I call it div curve, in fact. Okay. So it's minus d2 comma d1 dotted with u1, u2, and it's the scalar quantity du1, u2 minus du2, u1, d2, u1. Okay. So the 2D vorticity equation happens when you take the curl, the 2-dimensional curl of these equations, the Euler and Navier-Stokes equations, and this gives you this little system, very nice system. Scalar equation for omega. So omega is just the scalar quantity here, and it is transported and diffused by viscosity. Okay, so you have omega t plus u grad omega is mu Laplacian omega, coupled with the elliptic system, divergence u is 0, curl u is omega. Okay. Now let me do a calculation, which I believe everybody in this audience has done many times, but I want to call attention to some crucial parts of the calculation. So the energy for smooth solutions, the fluid domain without boundary, is obtained when you take the equations that model fluid flow and take the inner product with u and integrate. So you get ddt 1/2 integral u squared is this term here. Okay. It's a nonlinear, super nonlinear term minus integral of u dot grad u times u, and then the term with the pressure minus u dot grad p plus u times u Laplacian of u. And that can be rewritten as a divergence term minus divergence of u squared u over 2 minus divergence of up minus mu gradient of u squared. And that is equal to minus nu times the integral of grad u squared if everything is smooth and you have no boundaries. Now, what can go wrong? So first of all, smooth and viscid flows, u equals 0, conserve kinetic energy. Okay. Now, this is what can go wrong. this nonlinear term, u dot grad u times u. Okay, the rest, the pressure term, we can really throw away just by using, for instance, the Leray projector. That'll throw the pressure away. Okay, and the term with nu, u dot u times Laplacian nu. Typically, you have enough regularity to be able to do this integration by parts. So the crucial term here is u dot grad u. This trilinear term or this highly nonlinear term. Okay, if you look at LP norms of smooth vorticities, the fluid domain again without boundary, again you take your vorticity equation, you multiply by p 1 over p times omega to the p minus 2 times omega, and you get this. Get dBt of 1 over p integral over omega to the p is minus absolute omega to the p minus 2 times omega times u dot grad omega plus mu omega to the p minus 2 omega Laplacian of omega. And we do it, we play the same game. We write the term in green as a divergence term, an exact derivative term, and we integrate by parts the Laplacian term. So we get minus nu p minus 1 absolute omega to p minus 2 times graded of omega squared. And of course, you can throw away the divergence term if you don't have any boundaries. So you get this dissipation of LP norms of vorticity. And if nu equals 0, you get these smooth flows conserve both kinetic energy and all LP norms. Again, you have to be aware here of this term. That's the term that you need more regularity in order to actually justify all these calculations.
It has no boundaries. You're assuming it goes to 0 at infinity, yes?
There's no infinity. I'm actually thinking about periodic boundary conditions. I will make that clear.
Okay, I just wondered why the div becomes just the evaluation at the surface of say times p. That's 0 because
U dot n is 0.
right. So that that's
Okay.
yeah.
Yes. But
Yeah. Okay.
if you don't have any boundary,
That's fine.
all right. Okay, so the treatment of these two terms is completely different. Okay? In the case of vorticity, we need to make use of the transport structure for the equations, the fact that it's a scalar equation, so this is really only for two-dimensional flow, and the Biot-Savart law. In the case of the velocity, we need scaling arguments, critical spaces, and vanishing viscosity. Okay, those are the ingredients. Yes.
And last thing, you just go back just very briefly the previous slide. Just sorry. Oh, those are okay. And I'm sorry, but why did you decide to do L2 for u, but then LP for omega?
I have no better estimate for velocity.
Oh,
Okay.
okay.
Only L2.
You only have L2 for velocity, but you hope to do better for omega?
For omega, I will have, okay, so
Or
in the
worse or
case
something.
equals 0, I have a scalar transport equation by divergence-free vector field.
Okay.
Okay. Any what we call rearrangement invariant norms are preserved by the flow.
Actually, any function of omega is preserved. Any function.
Yeah, not only functions omega. Yes.
Okay, so we'll
Okay. So it is of interest to consider LP norms for P in general. We'll see actually later that these things are connected. Okay. And unhappily, the connection only goes really in one direction. Okay, so all right, let's go to the Untitled conjecture, which again, this audience knows very well. Okay, so anomalous dissipation is a cornerstone of turbulence theory. It corresponds to Kolmogorov's zeroth law of turbulence. And basically, it states that inviscid fluid flows which do not conserve energy should exist. The dissipation rate should not vanish. So turbulence is connected to anomalous dissipation, which, from my previous slide, it requires non-smooth flows. In 1949, Nussenzveig conjectured that anomalous dissipation could occur for flows that were less than a third regular. And eddy flows that were more than a third regular conserve energy, conserve kinetic energy. Okay, research on the Alzheimer conjecture developed along two fronts, flexibility versus rigidity, and I will offer you a brief history. All right, so along the direction of flexibility, it led to the development of wild solutions, which exhibit anomalous dissipation. Things started off with this work by Vladimir Scheffer in absolutely unreadable paper, which I actually did a review for Math Reviews back when I was just very young, shortly out of my PhD. So I was a student, but just shortly out of my PhD, and it was completely unreadable. So Sasha Schnurman in 1995 basically rewrote Scheffer's result based on physically inspired arguments, like entropy bubbling up, the inverse cascade, entropy bubbling up from smaller scales, and you obtain the same result, namely L infinity, L2 in time, L2 in space. Solutions of the order equations which were compactly supported in space and time. Bad thing about this result was that this was not the correct energy space, which was L infinity L2, and then it took until Camilo Deleuze and Laszlo's work in 2009 to obtain a solution which was actually the right physical space, the right energy space, and even more than that, it was actually L infinity in space and time. So they produced a solution which was L infinity in space, L infinity in time, compactly supported in space and time. Of course, with time-dependent energy. Okay, then Laszlo and his work led to a flurry of activity. And basically, this was improved. From L infinity solutions, they got C0 solutions, then they got C0 1/10 solutions. And finally, 4 years later, Bill Isat in his PhD thesis obtained solutions which were C0 1/5 minus epsilon. So get a little closer. I'm sorry.
Now you're in 3 dimensions?
Yes, everything here is in 3 dimensions. This is a brief history of everything here is in 3 dimensions. And actually, I will call attention to what is strictly 3D and what can be 2D or 3D and what is strictly 2D. Okay. So Phil Isat did this C0 1/5 minus epsilon, followed by similar result by Buckmaster, Deleuze, Isat, and Zakidi, where they produced energy prescribed flows, which were C0 1/5 minus epsilon. Okay. And then in 2016, Tristan Buckmaster, Camilo Deleuze, and Zakidi produced solutions which were in the right space in physical space, but still only L1 in time. So these were solutions which were almost everywhere in time, almost a third regular. And they were again leading to anomalous dissipation. These are all 3D constructions. The first 2D construction came out, as far as I'm aware, in the work of Antoine Chauffreux in 2013, where he produced a solution in C0 1/10, which with anomalous dissipation. Finally, in 2018, Phil Isat closed the Alzheimer conjecture based on the work by Laszlo and Sarah Deneri. Particularly Deneri, the Mikado flows, he did the gluing of these from one constant to another and produced solutions which were in the right Alzheimer space. So they were up to a third regular in space and time, compactly supported in time. This was followed by work by Tristan, Camilo, Laszlo, and Vlad Foucault from 2019, where they got the same result, but now with prescribed energy. Okay, and then Tristan and Vlad produced a viscous flow with prescribed energy. This is a very surprising result, okay, which they managed to extract an inviscid limit, which had anomalous dissipation. Little itty bitty if here, which is that the Buckmaster Foucault solutions were only Leray solutions, only distributional solutions. They did not obey the energy inequality for all pairs of times S and T. Okay, their construction is straight in 3D and it does not work in 2D. There's just not enough space to make this
Can
construction
you
in 2D.
explain the existing inviscid limit of dissipation?
Sorry,
I don't understand the statement.
they produced a solution of the Euler equations,
Yes.
which is a vanishing viscosity limit of these solutions that they have with prescribed energy profile.
The solutions are not gradient in the group, and you don't have dissipation energy. Doesn't make sense to dissipate energy.
The point is that the limit solution does not have constant, does not have conservation of energy in their work.
I mean,
They do manage to take the inviscid limit.
if I could remember well, solution they construct, they don't have vorticity or gradient in L2
So the whole issue of dissipation
Yes, but
anomaly
the
is,
velocity is relative.
dissipation anomaly is to show that the mean rate of dissipation of energy does not go to zero.
There is no rate.
I am referring to
Yeah,
almost
there is
dissipation in this
density.
broader sense,
Derivative
where
of
you don't have
dissipation.
conservation of energy.
That's okay. It doesn't matter. Just it's a bit of terminology. That's fine.
Okay.
Just was trying to understand. Because their solution was so weak that you cannot
Yes.
make sense of dissipation of energy, period.
No, I agree with
That's
you.
what I'm saying.
I agree with you, but
She's still
the term
not
anomalous dissipation has been used in this broader, more generalized sense, where for instance, you say that even the Scheffer and Schneemann solutions had anomalous dissipation because energy is not conserved. It's not dissipation. Okay. All right, there's this new 2D result by Navier-Stokes from last year, where they produced non-uniqueness for 2D Euler with vorticity and L1 infinity. And this is not, strictly speaking, connected to the issue of anomalous dissipation, but it is a non-uniqueness result. Well, in this broader sense, they don't actually look at, I'm sorry, it is an anomalous dissipation in this broader sense, and that their solution starts from zero velocity and it winds up with zero velocity. Okay. Their result is by convex integration, and I want to stress that their space, the Lorentz space L1 infinity, is not a subset of L1. It's not the L space hierarchy. Okay, and finally, last year, again, Albritton, Reid, Colombo produced non-uniqueness of Lorentz solutions. But this is with a four-signature.
What is the lower?
Sorry,
What is the definition of the lower solution?
what is
The
the
difference, what do you mean by lower out solution?
solutions which satisfy the energy of the polygon?
You classify that,
The energy of the polygon.
But they have force,
Yes,
special kind of force.
yes, a singular.
it's a singular force. And they have the inequality or the gradient is in L.
Yes.
What is in L1 and L2?
Okay, let's talk about the opposite direction. The rigidity. So first result was obtained by Frisch and Salem, 1975. The solutions of the Euler equations are L infinity in time, H5/6, that's W5/6, 2. Then energy is conserved. Then we have A Inc. 1994, who asks for a little bit more than L3 in time, C1/3 plus epsilon. And finally, Constantine TT, 1994, L3 in time, B1/3 plus epsilon, 3 infinity. State of the art is due to Sheskidov, Konstantin Friedlander, and Schmidtpoint, who proved in 2008 that if the solution is L3 in time, B1/3, 3, 0, then you have conservation of energy. And B1/3, 3, 0 simply means that the Lipinski components vanish as the frequency becomes higher and higher. This is a 3D and a 2D result. Okay, a strictly two-dimensional result was obtained by Duchamp-Robert in 2000, where they proved that if the initial vorticity is at LP, P is greater than 3/2, then energy is conserved. And actually, you can extend this all the way to L3/2 by the Sheskinov-Konstantin Friedlander-Schmidt-Coy result. Okay. All of these results involve optimal conditions for the energy flux to vanish. All of these results look only at the Euler solutions, at the inviscid solutions. They don't care about vanishing viscosity. Okay. Let me talk a little bit about scaling and define Onsager critical spaces. Okay, so the energy flux term that we're bothered by is this integral in time and in space of u dot grad u. Okay, the dimensions here are u over L to the n times time. In other words, u cubed L to the n minus 1 t. Okay, so I'm going to use a terminology introduced by von Schmidt-Coy of what are Onsager critical spaces. So B is an Onsager critical space if the B norm raised to the third power has dimensions which are u to the u cubed L to the n minus 1 t. Okay. So this is a kind of an informal definition, but we have some examples of Onsager critical spaces. So in 3D, L3 in time, L9/5 in space, velocity. L3 in time, H5/6 in space. In 2D, L3 in time, L6 in space. And L3 in time, W1 3/2 in space. And in any dimension, L3 in time, W1 3/3, 3. L3 in time, B1 3/3, 3. P for any P between 1 and infinity. And I want to emphasize these spaces. L3 in time, H5/6. So in space, this is the critical regularity in the H spaces. And that's the regularity of the first rigidity result that I mentioned in my previous slide by Frisch and Soler. So they looked at L infinity in time H5/6. Actually, the spatial criticality was attained. Okay. This other space, L3 in time, W1 3/2, well, we have this Duchamp-Robert result. The vorticity is an LP, P larger than or equal to 3/2. You could take equal because the Sheskinov et al. Result. Okay. Then that means that the velocity is actually W1 3/2. So indeed, that is the critical space, W1 3/2. Okay, in 2D. And here we have the B1 3/3, 3 infinity space, which is critical again in any dimension. Okay. Now let me talk a little bit about weak solutions. So for now, I'm going to take the fluid domain to be the torus, and I'm looking at 2D Euler on the torus, which is just yes.
Maybe you'll show it later. Can you go back to this first? Sure. I think the motivation for Schmidt-Coy was more involved in the energy transfer rather than this term. The flux is not from this term, but the flux is in shells. Because this term in principle is supposed to be 0. Like I tell you, what's the critical exponent for u cubed minus u cubed? U cubed minus cube is 0, so there's no critical. So, but when you look for quantities which is possibly not 0, like in the energy fluxes in the shells, then these spaces will play a role, but not from this particular term.
I beg to differ. I will show this, and there's a calculation which I will show this.
Okay, but what's the critical space for x cubed minus x cubed? X cubed minus x cubed.
The point is,
it is 0,
is that this is supposed to vanish if you can make sense of this. Okay, and these are critical spaces in which you can make sense of this, and you can estimate. Okay, so like I said, so I'm going to take 2D Euler on the torus with initial data in L2 and 0 forcing. And I'm going to be interested in weak solutions for which the vorticity is pth power integral for some p greater than 1. Okay. One relevant fact here is that wild solutions, all the wild solutions that have been constructed, all of them, they have no control on integrability of vorticity, none of them. Okay, so here we have a definition of the weak solution. So I'm going to take initial velocity at L2, initial vorticity at LP, P greater than 1. Okay. And I'll say that you have a weak solution if for every test vector field, which is divergence free, when you hit the equation with a test vector field and put all the derivatives onto the test vector field, you get this identity. Okay. And the divergence free condition is attained in the sense of distributions for almost every time. Okay. Now, existence of these weak solutions is known. The case P equals infinity was proved by Udovich in 63. DePerna and Maida in 1987 proved the case P greater than 1. Vecchi and Wu proved the case P equals 1, and it's also mentioned, its validity is also mentioned in the lore. And uniqueness is open except L infinity and nearby. Sure, there is the Brouet-Colombo result, but that's not in the same scale of stasis. It's not an LP. Okay. We're going to call a weak solution conservative if the L2 norm of the velocity is conserved, is constant in time. So here's our baseline result. We fix it positive time and a weak solution whose curl is an L3 halves. Okay, then U is conservative. And moreover, the local energy balance law holds. So this result is contained in Chesky-Ahmed-Ali because L1, L infinity, W1 3 halves is contained in L3, B1 third, 3 CZU. But we're going to outline here a totally elementary proof. Okay. So the proof is basically what you do always, you take a convolution of Euler with some modifier, or in the words of last week's talk, a low pass filter. And you have the smooth version of Euler, so U epsilon is now smooth, okay, and it satisfies dt epsilon U epsilon guide U epsilon is minus beta pressure P epsilon plus a remainder term, a residue term, which comes from the commutator. Okay. All right. If you multiply this equation by U epsilon, take the inner product, and look at what you're left with. Since U epsilon is smooth, you can just rewrite these things, differentiate at will, okay? And you get this equation 3. And the objective is to show now that each of these terms converges when epsilon goes to 0 to the corresponding term without the epsilon. Okay. Okay. So we have the first term with temporal derivatives, the second term again, and the third term is going to converge in L1. Okay, so A and B are subcritical for L3 halves. They only require L6 over 5. The last term, the energy flux term, requires L3 halves.
Which the energy flux term?
Sorry?
Can you show which one? Sure.
The last term is the one with the residue.
Okay, so
It's
not
U
the-
epsilon times the
that's exactly was
commutator.
my point. And it shows R epsilon.
Our epsilon is
It's the
commutator
difference.
between-
This is that it scales correctly when you multiply by U, and it is not 0 originally. That's exactly the point of us talking about the motivation for the scale. Is the R epsilon times the U epsilon. That scales correctly, not
Yes,
the U.
but that's not, I'm not doing this in shells.
As I said, the fluxes, because you do, when you do multiply by C epsilon, this is basically you doing type filter.
Oh, okay. You're Fourier transform. Okay.
Anyways, I mean, that's basically was my point, which is it's correct. It's like what-
Okay,
just basically mentioning where the motivation of Schwitzkoi came from,
okay.
at least my understanding.
For us, it's an issue. Okay, so I will show you eventually, fast forwarding this a bit, okay, that we get energy conservation if you're a vanishing viscosity solution, if the vorticity is an LP for P larger than 1 and less than 3 halves. So it's super critical. And then again, you're not doing this It's not in shells. All right,
But what's a
Let me go forward.
mollifier and what is this side
I'm
thing?
sorry?
What's a mollifier and what's this side thing?
this, you can think of this as just a low pass filter. That's what we're,
All right,
okay, so, anyways, where was I? Yes. Okay. So the flux term, well, by the regularity, all you need, you want the flux term to converge to 0 in L1. Okay, so U epsilon, omega epsilon is assumed to be, the vorticity is assumed to be in L3 halves, okay, which by somewhat of embedding gets the velocity into L6. So the dual to that is L6/5. So what I want here is the R epsilon, the residue, to converge to 0 strongly in L6/5. Okay. So let me measure this in L6/5. All right, and I just add and subtract the right amount of things, okay, and use things so I rewrite this term by adding and subtracting U epsilon grad U here and here, okay, and then adding and subtracting. Yes, U dot grad. Okay. So two things that I have to add and subtract. Okay. And the next thing to do is to say, okay, this guy is bounded in L6, okay, and this guy here is bounded in L3 halves. All right, so I'm exactly in the position where I can estimate this by L6 times L3 halves. L6/5 norm is bounded by this. Okay. Similarly here, I've got L6 times L3 halves, and here I have just L6/5. Okay, now what happens? This guy here is bounded, and this vanishes because modifications converge in Lebesgue spaces. All right. Okay, so modifications converge, this converges, and finally here I have the modification of the U dot grad U term, and U dot grad U is in L6/5. So just using properties of modifications, they converge in Lebesgue spaces together with Sobolev embedding. Okay, so the key fact is that U dot grad U times U dot grad U is L1, and the L1 norm is bounded by W1 3/2 cubed. So key fact here is exactly that this W1 3/2 is Schwitt-Quick critical. Now, now let's address Idris's issue with the shells. Okay, so the next step is to show that this P equal 3/2 is the optimal for this argument. We'll prove this rigorously. Okay, so the proofs of conservation of energy, they rely on these scaling arguments. And to show that the exponent 3/2 is optimal the argument above, we simply construct a vector field which just fails to be W1 3/2 and for which this energy flux doesn't vanish. So we go back to a little Cayley truncation. Here it is. Okay, so we just truncate at scales 1/2 to the q here, up to 1/2 to the q, and then this is just another low pass filter, okay, and therefore it's smooth. Okay, and we can argue easily that the energy flux for SQ vanishes for F in W1 3/2. It's the same kind of argument that I made before. Now, if I test the order equations with this guy, SQ of SQ of U, then the energy conservation is equivalent to showing that these energy fluxes, and now you're measuring this through the correct scale through the shell, 1/2 to Q, that this vanishes on average in time when Q goes to infinity. So here's the theorem. There exists a divergence-free vector field in V1/3 infinity in W1P for any P less than 3/2 for which this guy does not vanish. All right. Now, what this tells us is that this argument cannot be extended beyond P equals 3/2. It's something that we already suspected for a multitude of different reasons. So the divergence-free vector field is not a dynamical example. This is important. It's not a solution to Euler equations. And so we pose ourselves the question, B meaning Roman-Schmidt-Coy, Alexei Sheskinov, Hilton Lopes, and myself, we pose ourselves the question, is there a weak Euler solution in 2 dimensions with some kind of control on the durability of vorticity and which is not conservative? Okay, that's the question. And the corresponding question can be posed also for vorticity, for the vorticity equation. Is there such a weak solution for which the vorticity is not transported, or maybe for which some of these quantities, these supposed conserved quantities, are not conserved? Is there some kind of Lagrangian structure that we can preserve here? Okay. Now, from Krashen's 2D turbulence theory, we know we expect in 2 dimensions to have a forward entropy cascade, which means that somehow there is supposed to be a regularizing effect 2D coming from vanishing viscosity. Okay. So this suggests that there is some kind of dynamic mechanism that prevents anomalous dissipation in 2D. And even for supercritical flows. I put less of the third regular, but I actually mean supercritical in this Schmidt-Coy criticality sense. Okay. So let me define my the kinds of weak solutions that I would like to be discussing. There are the vanishing viscosity solutions, and which we also call physically realizable weak solutions. So U is a physically realizable weak solution of the crustal Euler equations with initial velocity U naught if, first of all, it is a weak solution, and second of all, there's a family of solutions of Navier-Stokes which converge weakly to it. So it is attained as a weak limit of Navier-Stokes solutions. Okay. The initial data for these Navier-Stokes solutions is supposed to converge strongly to the initial data for the Euler equations when we're interested. Okay. A family which satisfies this is called a physical realization of U. Okay. So first theorem that I want to mention, which is joint work with Alexei Sheskinov, Hilton Lopes, and Roman Schmidt-Coy, and it's a fairly old theorem at this stage, okay, says that if U is a physically realizable weak solution of the Euler equations, for which the initial vorticity is pth power variable for some p greater than 1, any p greater than 1, and if there is a physical realization for which the initial vorticity is bounded in the same LP, then this weak solution conserves kinetic energy. Even though it's not in critical space W1/3/2, it's going to be less regular than W1/3/2, and therefore this is a supercritical result.
You mean bounded independent of sorry, you mean bounded independent of
Sorry?
bounded is independent of
Bounded independent.
Bounded independent of U, yes. Okay, this is not asking much, actually, that omega naught mu is bounded in LP, because first of all, I can set omega naught mu whatever I want. And one, two trivial ways of doing this is, first of all, take omega naught mu to be constant equal to omega naught. Second, take omega naught mu to be some kind of low pass filter on omega naught. It's a modification of omega naught. Both of these will lead to bounded in LP. Okay, so I'll give you the proof because it's fairly simple. Okay, so first of all, I'm going to assume that omega naught is not an L2. The initial vorticity is not an L2, otherwise the whole thing is trivial. Okay. Okay. Now U is supposed to be a physically realizable solution, so I'll take a physical realization, U nu, with omega naught mu bounded in LP. The vorticity equation, we've already met it before. Here it is. And since I have no boundaries, since I'm on the torus, periodic boundary conditions, this is a perfectly reasonable equation. I can multiply by omega nu and integrate on the torus, and I get the equation for the dissipation of entropy. dt of omega L2 squared is minus 2 nu gradient of omega naught nu, omega nu L2 squared. I'm going to use something called the Galliard-Navier inequality. states that for any t between 1 and 2, I can interpolate the L2 norm of omega naught omega nu with the gradient of omega nu in L2 and omega nu in LP, and then there are some powers.
And that doesn't depend on omega being a vorticity, that's just true for functions with that regularity.
Yes. Okay, so because I have a minus sign here, I can just invert this whole thing, and this is what I get. I'm leading to a groundball differential inequality. And then I recall that the vorticity, I showed you that for smooth solutions, the LP norms of vorticity are conserved, but we also have seen that the LP norm, the last term with the viscosity on my second slide, second or third, forget which side, okay, there was the dissipation of the LP norm was a negative quantity. It was a minus sign. Okay, so the LP norm of vorticity at time t is bounded by the initial LP norm, which is bounded by hypothesis. And of course, it's not equal to 0 because I assume that my initial vorticity was not in L2, so it can't be 0. Therefore, I get ddt of the L2 norm squared of vorticity is bounded by minus 2 nu L2 norm of vorticity to this power 4 over 2 minus p times something which is going to be bounded. So I should have written C not nu here, but just taking something bigger than all of these guys. Okay? So if I rewrite this for y of t, and then I get this differential inequality. Y prime is less or equal to minus 2 C naught nu y to the 2 over 2 minus p, the 4 over 2 minus p, 2 over 2 minus p, because I have the energy, the inequalities for omega L2 squared. And this exponent of y, 2 over 2 minus p is greater than 2. That's important. So I integrate this in time, starting from some positive delta, because I do not know if omega naught nu is bounded or not in L2. All I know is that it's bounded in LP. So it could be initially infinite, which it is at 0, or it could not be infinite. It is going to go to infinity when nu goes to 0. And I get omega t minus whatever I get, y of t to this power minus p over 2 minus p, y of delta to this negative power, and this quantity here with a positive power of the limit delta going to 0. You get this. You take the limit here, so now you're going to get omega, the L2 norm squared of omega nu is bounded by nu times t to this negative power here, and this omega naught. If omega naught nu L2 is 0, is infinite, this term disappears. Okay. Otherwise, it's there. It remains there. Okay. Now remember the energy identity for Navier-Stokes, which I rewrite in terms of vorticity, and I get this. Okay, so the gradient L2 squared is the same thing as the L2 squared. Integrate this in time and use the estimate for vorticity, and we get this series of inequalities here. U nu at time t minus u naught nu at time u naught nu L2 squared is negative, but it's greater than or equal to minus 2 nu integral 0 to t, and the estimate that we got for the L2 norm squared of vorticity. And then we integrate this and we get the result here. And I noticed that when nu goes to 0, okay, even if omega naught nu L2 is not infinite, it has to go to infinity when it goes to 0, because the limit omega naught is not in L2. So the L2 norm of the limit omega naught is infinite. Okay? And because omega naught nu is bounded in LP, that forces the L2 norm to go to infinity. So when I send nu to 0, this term here becomes 0. Okay, this term here goes like nu to a power 2, p minus 1 over p, and p is greater than 1. So this is a positive power. Okay, and this goes to 0. So my whole right-hand side here will vanish when it goes to 0. Okay. That's just what I just argued before. If omega naught nu is equal to infinity in L2, then we actually get a rate at which this vanishes when it goes to 0. All right. Either way, since p is greater than 1, the right-hand side of the inequality vanishes as nu goes to 0, and therefore you show that 0 less greater equal to something, greater equal to something that's going to 0. So the limit as nu goes to 0 of the L2 norm of u nu minus u naught nu is 0. Now, Dupert and Maida, when they proved their result, the existence of a solution forwarder with vorticity LP, p larger than 1, they observed that the corresponding vanishing viscosity velocity will be compact in L2. Therefore, it converges strongly in L2. Therefore, this is called a non-concentration result. Therefore, the limit when u goes to 0 of the L2 the kinetic energy, the viscous solution is the kinetic energy of the Euler solution. I also assumed in the definition of physically realizable weak solutions, I assumed that the initial data converges strongly in L2. So this guy here converges to the initial data for the Euler solution, and this guy here converges to the L2 norm squared, the energy for the Euler solution.
Can I ask you, are we in 2 dimensions? Or
sorry.
are we in 2 dimensions or 3?
Yes, everything occurs to everything. All right. Yes.
Do you have a counterexample when omegas
I'm
are 1?
sorry.
Do you have a counterexample when omegas are 1? Do you know what happens?
No, this is a big problem. This is basically, the end of this lecture series will finish with everything that we don't know what to do for omega 1. Okay. All right. So this story of concentrations versus kinetic energy, conservation of energy, it starts with the work of Ron Dupert and Eddie Maida back in the late 80s. They were looking at sequences of approximate solutions to the Euler equations. And the first thing that they noticed was that, well, if the sequence is a nice sequence and converges weakly to the Euler solution, then because of lower semi-continuity of these L2 norms, the energy for the Euler solution is less than or equal to the limit of the energy of these UNs. It's approximation. Now, they noticed that the fact that if the approximations are conservative, that does not guarantee that the weak limit is going to be conservative. Okay. And what they postulated was the convergence is not strong when you have energy defects for the weak limit. Okay. So their idea was that energy could concentrate in small scales and disappear in the weak limit. That was the idea behind what they were thinking. They were looking specifically at the problem of justify or rigorously establishing the evolution of vortex sheets. Now, if you have conservative approximations plus non-concentration, in other words, if there are no energy defects, okay, then a conservative solution, this will apply a conservative solution. In other words, of course, okay, if this less than or equal sign is an equal sign, okay, and actually there's no limit here, so that you don't have any energy defect, that's a non-concentration. Strong convergence, then if you have a conservative approximation scheme, then the limit will also be a conservative solution. So everything that we were looking at before was dealing with the fact that we were not a conservative approximation scheme. We're a Navier-Stokes approximation scheme, which is inherently non-conservative. So what are good approximation schemes? What kinds of approximation schemes did they look at? Mollifying the initial data and exactly solving the Euler equations with smooth initial data that generates a good approximation scheme. Something called the vortex blob approximation, which is the approximation by a numerical method, the vortex blob method. Truncating the initial vorticity and then using solutions Udovich. So L infinity weak solutions. Vanishing viscosity is all good, also a good approximation scheme. First three, for this one actually, and the universal solution are conservative solutions. The blob approximation is conservative, but for a different Hamiltonian. Okay, so Dupert-Amida, as I mentioned before, they were interested in the existence of solutions with vortic sheet initial data, which means vorticity, the bounded measure, which is an H-1. Typical example of this is a Dirac delta sitting on a curve. So a vortex curve. Okay. First, they proved if omega naught is LP, P larger than 1, there exists a solution. That's their result from 1987, which I mentioned before. And the proof is simply that if omega naught is an LP, then the vorticity is L infinity times LP by any of these approximation methods. Therefore, the velocity is at W1P, and W1P is compactly embedded in L2. So you get a compact sequence in L2 for the velocity, which means there's a subsequence which converts to strong. That's enough to produce a weak solution. All right. They also needed that some control of the time derivative, very, very weak control of the time derivative. Okay. Their proof was for velocity formulation of the order equations, and it doesn't work in L1. So the question is, what did it take to get things down to L1? Transfer of information between vorticity and velocity. It's complicated. So if omega naught is L1, this required revisiting the vorticity formulation, plus doubling dimension, plus a symmetry argument. Now I'll show you very briefly what's involved just for kicks, but we're not going to be really looking at this much again, except to have this in the back of our minds. So now there's a theorem by Jean-Marc Delors in 1991 and then Becky in 1993. So Delors proved that if the initial vorticity is a bounded measure with a sign, the distinguished sign, what this means is the flow rotates only in one direction. It's only allowed to rotate in one direction. And then Becky Wu took initial vorticity, which is an L1. So actually this became a theorem that said initial vorticity is a non-negative measure. The singular part is a non-negative measure with a distinguished sign, and the continuous part is an L1. Then there's a weak solution. The proof involves this revisiting the vorticity formulation. If you look at the vorticity equation, the nonlinearity is U times omega. Okay? And that's bad for vorticity in L1. Unless you rewrite this nonlinearity using the Biot-Savart law. So you have the nonlinearity, U times, phi is just a test function, times U dot grad omega. So you throw the derivative onto your test function, and here's your nonlinearity, U times omega. That's bad if omega is L1. You can't define this as an invariable function. Instead, you substitute the Biot-Savart law. U is K involved with omega. K is x minus y perp over x minus y squared. So I write this out as a double integral, and here's my double dimension. So it's minus gradient of 5x, kx minus y, omega x. I switch the roles of x and y here, and I notice that if I switch the roles of x and y with k, I get a minus sign. So this k is antisymmetric. So I take half of one plus half of the other, and I kill the singularity. That was Delors' main observation. Actually, it was Chauchet's observation. K is like 1 over z, and the singularity gets canceled by the difference in test functions. Get an extra x minus y over here, which cancels the singularity of k of x minus y. Except on a diagonal. Everything works very nicely, except if you're on the diagonal. And actually, you can ignore the diagonal if you have no concentrations in vorticity. Instead of looking at concentrations in velocity, this argument needs to avoid concentrations in vorticity. So it works as long as the total mass of the vorticity on small balls vanishes. So there are no direct deltas vorticity. All right, bottom line, you need more from the vorticity equation to get a result for P equals 1. And that is what we're hoping for, to be able to extend the energy result to P equals 1 and even to bounded measures. So more about that on Wednesday. Actually, more about that on Thursday. Wednesday, we're going to talk about something a little bit different. Thank you.
Very nice. Questions or comments? In the audience, do we have anybody who did not reply? Nobody wants questions? Sergey, are you satisfied?
It was too fast.
I will close the slides.
Yes, very good.
Thank you very much.
Very good.
Hi, Idris.
Uh,
Hi, Idris. This is Anna.
Yeah,
I have a comment more than a question. I just wanted to comment on Maria Colombo's and others. I want to say that the forcing is not that singular because it's a one in time, which is the right regularity for Mal's solutions. But the main issue is that the forcing depends on the solution. I just want to make a clarification. So the forcing is basically the right-hand side of the solution for one of the two solutions they construct.
This.
Kind of wondering this through it. I think I know the answer, but can you talk a bit about the structure of the nonlinearity with in transport equations and things like this for omega? It doesn't really show up in a velocity equation. You just need scaling arguments. But how much of the program goes through? I think all of it. If you, instead of using u dot grad u, you replace the nonlinearity with like omega cross u and get a modified Bernoulli pressure. Right? There's this identity where you,
So after.
yeah. So right, I'm just wondering about the structure. How much relies strictly on the structure of the nonlinearity? Right. So normally have u dot grad u, the nonlinearity.
Oh, I see. Okay.
You can replace it with
If
this.
if you look at u cross omega,
Yeah,
thinking
for
at
example.
3D. You don't have any estimates from me.
Yeah.
That's the problem.
Well, you can do this in, you can do a similar thing in 2D.
Oh, sure, yeah.
And it's just, it's nothing that's relying on a particular structure of
That's
the
right.
nonlinearity, right? It should
That's
go,
right, yes.
it's more to have things scale.
I guess what's he's saying, sorry, instead of talking about nonlinearity this way, you can think about it like this modular pressure.
Yeah. That's
And
right.
now when you dot with u integral here, you have a problem, but when you dot with u here, it's automatically zero. That's what I was saying, that
I see.
the issue is on at the flux rather than.
But you're thinking 3D. Because if you do this in 2D, you have
But this is even 3D, 2D doesn't matter.
Yeah, in 2D you get
2D, you're gonna get
scalar
U
omega times the perp of u.
You're gonna u omega there, 2D.
No, you have
No,
this
you get
term
perfect-
plus another
perfect.
for the depression.
Perp of u is geometrically.
No, this nonlinearity is the same type plus gradient plus 1/2 gradient.
Oh, okay.
So this nonlinearity are the same algebraically for classical. So if you dot here, at least algebraically zero without integration, without making sense, you have to make sense of the product. That's basically. But the other observation with R epsilon became clear. You need the scaling. That's what I said. That's what Schmidt-Coy motivation, and it was also clear later when he spoke about how the Littlewood, the decomposition.
The little Paley.
The Littlewood Paley decomposition. It became clear that the fluxes there, you need them to make sense. So that's where then the scaling comes naturally, because these quantities are not really zero. You want them to converge to zero. The same way you wanted the R epsilon to converge to zero.
I see.
But nonetheless, it's okay.
So can I, okay, so what you're saying is true. And you.
With minus sign.
And you,
No, that's the correct sign.
you add
Oh,
this
yes.
extra half u squared into the pressure.
Yes, yes.
Okay, so in other words, you're looking at Onsager rough solutions, you're transferring the problem of integration from there into the pressure term. It must still be there. I mean, what you're saying is that, of course, geometrically, that's always true. That dot product is zero.
Sure.
But you haven't really got rid of the pressure of non-integrability of that term. You've just transferred it to the pressure. You must have done.
You have gradient of u square now.
Yeah.
Yes, and
Well, all I'm saying is I'm trying to understand it. You start with a problem, you haven't got rid of it, you've just moved it somewhere else.
yeah, I understand what you are saying, but I can say God defined Navier-Stokes equation, the UdP minus u Laplacian u plus omega cross u plus gradient of q equals to 0. This is, and now div u equal to 0. This is my Navier-Stokes. Doesn't matter what's inside the q.
Well, I was thinking
And
of Euler.
Well, okay, so I erase that.
Yes, I know. But when you're, but the whole point about the Onsager thing is that you can't, you've got problems integrating that top term. The problem hasn't gone away simply because you've rewritten it. So you've moved the problem somewhere else.
That will appear if you do a low-pass filter on that term,
Yeah.
multiplied by what's.
No,
Because
how
then
do
it's
you
no
know-
longer, identically. So,
How do you know that a rigid
yeah,
pressure term was
It was not the same problem, same pressure.
It's a gradient of some scala, which is unknown. How
Yeah, it's the same. It's the same way you face the original pressure, you will face it the same way.
Yeah, sure.
So, but anyway, so it's not like the issue of like you transfer the problem to another thing. It is a new pressure, modified pressure, but the original pressure suffers from the same lacking. Anyway, this is just an observation that Schwitko, my point is that I know the way he thought about it, more about fluxes rather than about this particular, but nonetheless, it starts from here. Starts from here. That's basically was my simple comment. Because they are all the same structure. Yes.
With these physically realizable solutions, do you have any results free?
Best that you can do is there is some work by Camilla Nobili and Christian Seitz for axisymmetric solutions, but it's a little bit unsatisfactory. What they get.
Well, since you brought up the subject, Claude Bardos, sitting next to me and myself, we introduced criteria called ruling out.
I know, I'm going to mention
You
it.
know, but you didn't mention it.
No,
We call it ruling out.
I am going to.
Okay,
But
ruling
it's
out,
not-
basically, instead of doing physically realizable, we were less ambitious and we said any weak solution of Euler, which is not weak limit of Lerehov weak solution, should be ruled out. Doesn't mean it should be, the others are, but should be ruled out. And in the paper, which is your co-author, Bardos and myself, in which we looked for a 2D Euler as limit of 3D of equations. Otherwise, I mean, like with the symmetry, blah, blah, blah. So it's not nobly axisymmetric. We did it for axisymmetric.
He didn't mention it
it's
because
just-
he's saving the
It's not
best
the
for
conduct of
last.
energy. But I didn't forget, I was going to mention it in my lecture too.
Sorry, I
Best for last.
ruined it for you.
It was going to be a surprise. What did you do?
Very good. I think probably we're done for today. There's a drinks for the other party. Let's crash the party. I'm supposed to be there, but I'm not. Let's crash the party. Thank you. So we continue on Tuesday, on Wednesday.
Wednesday.
It's